All right, guys, these are going to be the inertia notes, and so we're going to start off with kind of a review. So we have this object that is resting on this inclined plane. So it says draw a free body diagram that is going to show all the forces that are acting on it. And so key thing here is that it is a stationary object, okay? So you should at this point pause the video and just sketch this out really quickly, and I'm just going to go forward. So when you're ready to go, I will walk you through it. Please take the time to just take a couple minutes and sketch this out. All right, so first off, if I look at this object, I know that this object has weight. Therefore, there is going to be a downward force vector, F of mg, which will be right over there. Okay, so there's my downward force vector. And then if I look at this thing, it is going to want to go, so there is going to be an upward force, okay? So normally if it were laying down flat, there would be an upward force from the normal force. Now that I've turned this way, remember that normal means perpendicular. So the normal force is going to act perpendicular to this slope, meaning that way right there. So there is a force coming outward right here, okay? And then there is one other force. If you think about this, it wants to slide down. So remember that there's a force that always is going to oppose the motion of an object, and we call that friction. So friction is going to oppose the motion, which wants to come this way. So friction is going to act in that direction right there. So those are the three forces that are acting on this object. But if you look at that, you'd say, well, if it's stationary, and we see that it is stationary, then it must be in equilibrium. And if it's in equilibrium, how can three forces put it in equilibrium? So again, kind of a review of our last unit, I can use the parallelogram rule here for these two forces which are not in the XY direction. And I can make my parallelogram, promise, okay, and then realize that the resultant vector is going to go straight up right here. And I can see that this vector here is exactly equal and in the opposite direction of this vector right here. So my forces are balanced right here, okay? And so that's the first one for right there. How does the normal force compare to the weight? Well, the normal force is actually less than the weight of the object. We have to look and see that some of the upward force came from friction, okay? So on a flat table, the upward force would equal the downward force, and it would all come from the normal force. But because this is tilted at an angle, the normal force is actually smaller, and some of that upward force is actually coming from friction, okay? What would happen if the coefficient of friction were altered? So we're going to be doing a lab called the Stinky Feet Lab. It's going to look a little different in the remote world, but I will video some things, and you will come to understand what this term coefficient of friction means. But basically, it's a ratio that tells us about how much friction an object is going to feel based on its weight. Okay, so now I'm going to scroll down here. So you saw a demonstration where air was evacuated from a chamber and a feather and a penny fell at the same rate. How does inertia explain why they fall at the same rate if they are exposed to the same gravitational force? That's a tough question. So I'm just going to outline this quickly, and we will discuss this a little bit more later on. But let's say I've got my penny. My penny weighs more than my feather. And again, I can't draw a feather. I apologize. But let's say the feather clearly weighs less than the penny. There is a greater downward force here. And if there's a greater downward force here, we would expect this to fall faster than this one. There should be a greater acceleration here than here. So we're going to use inertia as we go forward to explain why they actually both fall at the same rate. And I'll just give you a hint. There's a lot less mass here, so we don't need as great a force to get an equal acceleration. So we'll talk more about that as we move forward in the unit, okay? And then what role does inertia play in planetary orbits? So think about this. The planets are going around the sun. They're not being pushed by anything. So why is it that they continue to just move around in orbit? And the answer is inertia. Okay, we'll kind of see what we mean by that as we go forward. So again, kind of a review here. The English system is what we use in the United States, but the rest of the world is going to use the metric system. But you're going to find that you're probably more familiar with this when we talk about forces than you are this. So first off, in the English system, we weigh ourselves. We're familiar with that when we weigh ourselves in pounds. Okay, and then the mass one. This one is a really obscure reference here. So slugs is the unit for mass in the English system. When we get to the metric system, we measure weight in a force, which is newtons, and then mass is kilograms. Okay. So you are familiar with that. So I told you before that you don't need to memorize much in this class, but this is right here something that you are going to be using often, and you should memorize this. So 1 kilogram is 2.2 pounds, but these are both also equivalent to about 10 newtons. So when we are just doing our calculations, we'll use 10 newtons. If we're doing a lab, we'll use 9.8 newtons. Okay, so 10 newtons, 2.2 pounds, 1 kilogram. We're going to come back to that in just a moment. So again, we talked a little bit before about a newton is a kilogram meter per second squared. What does that mean? So 1 newton is the force felt by a 1 kilogram object that is accelerated at 1 meter per second squared. Okay, so if I have a 1 kilogram object that is accelerated at 1 meter per second squared, the force it would feel is 1 newton. So then we have this object over here. So this is a scale or a balance, if you will. And so the question is, does this object measure mass or does it measure weight? And so the way you approach that question is mass is a measure of like how much stuff is in something. So when we go from one place to another, if I were to take this bowling ball and I were to kind of look at it here on Earth, it has a certain mass. If I were to take this bowling ball to the moon, it has the same mass. It's still made of the same stuff. That didn't change. So mass doesn't change. If I were to weigh this bowling ball on Earth, put it on a scale, and then go to the moon and put it on a scale, I would see that that number does change because there's a different gravitational pull. So does this measure mass or weight? In other words, if I were to put an object on it here on Earth and then take it to the moon and look at it again, would it change? If it doesn't change, it's measuring mass. If it does change, it's measuring weight. The answer is, well, let's look at it. If I have an object here, let me actually pause and say, pretend I have a scale here and I have, so I've got an object here and I've got an object here, okay? So right now they're balanced. So the downward pull of gravity on this side is equal to the downward pull of gravity on this side. So because the gravity is equivalent on both sides on each object, it's balanced. If I were to then go to the moon, there would be less pull on this side. There would be less pull on this object, so gravity would be smaller. But it would also be smaller on this side. And it would affect both sides equally. So the ratio would be the same. So if I were to go to the moon, it would still be balanced because gravity would change for this equally for both sides. This object measures mass. So a balance measures the mass of an object. Whereas if I were to step on a scale, which uses a spring that gets compressed, my weight would change. So this measures mass. Oops, too far. Okay, so coming over here, so weight depends on, well, it depends on gravity, but it also depends on mass, but gravity. So when we change the gravitational field, we will change the weight of an object. And then we kind of refer to that F of g, and I like to use F of mg, but it's the force of mass times acceleration of gravity. The force of gravity is a mass in a gravitational field. Okay, that's why I like to write F of mg, but a lot of times you'll see it as F of g. So what does not depend on gravity? Mass does not depend on gravity. So here's a quick little question. The same force is applied to two objects, A and B. So we have this big car here, and we have this smaller car here. Which is accelerated more? So if I put the same force on both objects, which one will accelerate more? So I can't push the cars right here, but I can do a similar thing with my bowling ball here. So I've got two objects, okay? This one is like an air globe, and this one's a bowling ball. If I put the same force on these objects, which one will accelerate more? And hopefully you understand it's this nice light one. If I shake this one, it's much harder to shake this and move it than this, okay? So the greater the mass, the harder it is to accelerate. So this one will not accelerate as much as this one, okay? And then the attraction between two masses, that will be gravity. So microgravity, this is an interesting thing. So a lot of people think, you know, if you go to the International Space Station, the astronauts are floating around because there's no gravity. And that's not actually true. There is gravity on the space station. So why are they floating around? And so some of you have probably heard of something called the Vomit Comet. It's a plane that flies around and can mimic free fall. And so in other words, it can mimic no gravity. And so what happens is the plane flies, it goes up, 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 and then it dives down. And as it dives down, you are falling under the influence of gravity, but everything is falling around with you. It's kind of like if you went to the Tower of Doom at Elitch's, and when that cart falls, you know, if you were to hold a marker, and the instant that cart dropped, you will let go of the marker, it would fall with you. It would appear as if you were weightless. You're just floating around because this would tumble with you. And that's exactly what's happening in microgravity. It is a state of free fall. But then you say, well, the astronauts are not falling, and they are actually falling. They're going in a circle, and they're constantly falling towards the Earth. It's just that they're moving so fast sideways that as they fall around the Earth. It's a really hard thing to understand, but they are falling around the Earth. Okay? So microgravity is a state of free fall. So here's a quick question. We have two identical objects, and the astronauts on the International Space Station want to know which one has more mass. Could they figure that out? If they're exactly identical, could they possibly figure out which one is more massive? And the answer is yes, and I kind of alluded to it earlier. So let's say there are two spheres like this. They're identical. You know, texture is the same, everything is the same, but one is much heavier than the other. And the astronauts are in free fall, they're floating around. Could they possibly know which one is more massive? And like I said, the answer is yes. And the way they could do it is just shaking it. This one is much harder to shake because it's heavier than if I had something. Let's pretend this looked exactly like that. This is much easier to shake. It has much less mass. It's much easier. It's much more susceptible to a force. Okay. Come over here. Okay, so then the notes on this chapter, and this comes right out of our book, which we never use our book, but I just wanted to use kind of a nice, easy flow for you. So Aristotle on motion. So it used to be believed that there were two kinds of motion, that things either went up or down. And so they believe this because if you look at smoke, smoke rises. And if you look at other objects, say our pig that we weighed, it falls. Okay, so objects either go up or down. That was the natural state of things. Copernicus talked about the moving Earth, and so this was a big thing. Like one of the reasons people didn't believe the Copernican theory about the sun being at the center of everything is they said, well, if the Earth is going around the sun, we're traveling at 30 kilometers per second. That's pretty fast, and there is no possible way we could be moving that fast, because if we were, we would be like ripped off the earth. And so many people didn't believe that we could possibly be moving that fast. So then Galileo and motion. So Galileo really set the stage for this unit, which is inertia. And so he did a lot of trials, experiments using inclined planes, where he'd roll these spheres down these inclined planes. And he realized that, if you roll something down an inclined plane, it accelerates down. It goes faster as it rolls down. Makes sense. And then it slows down. It goes slower as it rolls up. But if you set something in motion on a perfectly horizontal plane, it will basically stay the same speed. So here on Earth, that's harder to see, because when we roll something, we see that it slows down after time. But if you think about it, if you went to the bowling alley and you roll a ball down the alley, that's a nice flat track, if you will. And that bowling ball, if you don't spin it, will go straight, and it will just continue to roll down the alley at basically the same speed. Eventually it will slow down, but it basically rolls at the same speed. And so no slope, it doesn't speed up or slow down. The only reason the ball will slow down is because we have friction. So friction will eventually slow that ball down. On something like a bowling alley, there's less friction, so it will go much further. But if we were to roll it here on on a rug or something, it's not going to roll very far because of friction. So what he kind of figured out is that if you rolled something down a track, it'll pick up speed here, roll at the same speed here, and then it will slow down going up. But it should go up to like nearly the same height as where you rolled it down from. Okay, friction will not allow that to happen, because it will go slower eventually, and it will go a little bit below. But in a pretty much in a frictionless environment, wherever you drop it from, it will go to, and then it will just keep on going back and forth. Okay, so the same is true if you kind of like change the angle over here and bend this down. It will roll down. It will slow down less quickly than it did here, so it will roll further and go to, again, nearly the same height. But Galileo said, well, what if you pull this down below the height it will roll to, and just made it go flat here? If you roll it down, it will just keep on rolling and go on and on forever. And that's basically what inertia is. So the diagram kind of shows inertia. So we've all heard what inertia is. So objects at rest stay at rest. Objects in motion stay in motion unless acted upon by an outside unbalanced force. And it's that end part which people tend to just kind of cut off, but that's the most important part. If something is just sitting there, this bottle is just sitting there, it will continue to stay there unless I come over and give it a push. If something is rolling, that bowling ball is rolling down the alley, it will continue to roll down the alley unless it hits something and stops, or friction acts on it over a period of time and slows it down. But if it were in a completely frictionless environment, if I were to go into space and throw a pen in the middle of nowhere, that pen would just keep on going on outward at the same speed, in the same direction, until it encounters an outside force. Okay. So coming over here, some Newton's first law of motion. So that basically sums up what I just said. You've all seen this, and I'm going to do a demonstration on this for you guys, where if the cutlery, the plates and everything is at rest, and you pull that tablecloth, this stays here because of its inertia. It wants to stay where it is, and you can pull out the tablecloth because this wasn't in motion. It wants to stay that way. A satellite like Voyager wants to continue outward, and it is continuing outward, and it's been going out for over 40 years now, and it will continue going in a straight line at nearly the same speed. Only slight variations in gravitational tugs from other things will affect it. So mass is a measure of inertia. So let's say you had a friend, it wouldn't be much of a friend, who gave you a challenge. And the challenge was, which object could you accelerate by kicking it the hardest? So you could either kick this bowling ball, or you could kick this globe. And hopefully you realize that you would want to kick this, because if you kick this, you're going to break your foot. Well, why is that? this is going to resist a change in motion. So when you kick this, it is going to exert a huge force back on your foot, and you're probably going to break your foot. And you're not going to accelerate this very much because its inertia resists that change in motion. This, because it has very little mass, it does not resist that change in motion. It'd be very easy to kick this, and it can't exert a very large force back on me. Okay, so you would want to kick a very light object, like in the picture here, he kicks the can, this guy kicks the car, and he hurts his foot. So mass is not weight. Again, it is not weight, but they are closely related. So here on Earth, we can take 1 kilogram, put it on a scale, and it would read approximately 10 newtons or 2.2 pounds. So the moving Earth again, and the Earth. So this is a kind of a thought question for you. So I'm going to start off here. You're in a plane, and you're flying in the plane, and you take he takes a penny. I'm going to take this pen. If I were flying in the pen at say 500, or flying through the air at say 500 miles per hour, and I take the pen and I throw it in the air, where will it land? Okay, so if I am flying, I have inertia, and my body wants to stay in motion because I'm with the plane. But what about this? When I throw it in the air, it has less inertia than me, right? So it weighs less, it has less mass. So when I throw it in the air, what will it do? And I used to have a skateboard here where I would do this. I would ride the skateboard. You wouldn't be able to see me because I go out of frame. But if I were to ride on a skateboard and throw this in the air as it was moving, it would look just like that. Because even though this has less mass than me, it still has inertia. And its inertia will carry it forward, because if it's in motion in the plane or on my skateboard as I move, it will continue in motion unless acted upon by an outside unbalanced force. So as you're flying in the plane, if you throw that up in the air, you're both moving along at the same speed. There's no outside force that's going to act on you, so it's going to land back in your hand. The same holds true with the bird over here. So even though the Earth is moving around the sun at 30 kilometers per second, when the bird drops out of the tree, he doesn't fly back way over here. The worm and the bird are both in motion, so the bird can drop straight down, just like when I'm in motion in the plane. If I were to drop this, we're both in motion, it's going to land right back in my hand. I just can't catch, okay? So